Hello students, this is Gwen in your chemistry class. I apologize for this lecture not getting up right away. I'm still locked out of the computer upstairs and I haven't had time to record it. So this is the lecture that I did on Wednesday. We're going to go over the first part of chapter 4, and then there's two handouts towards the end of week 3. And one is called Physical Changes handout. It's a PDF, and then there's a Chemistry 120 Chapter 2 notes that we're going to go through. And we did part of them on Wednesday, and we did lab today, which is Thursday, and we'll do the rest tomorrow. But first, I want to go through about half of Chapter 4, and we're going to stop when we get to atomic mass units because we want to concentrate on the ions and the bonds, and that's where we're and naming of compounds within the chemical reactions. That's where we're going to stop for the exam. That's going to be a week from tomorrow, which is October 16th. Okay, so if we look at what we've been talking about for the past couple of weeks, we've been talking about molecules and atoms, and what we've seen is that molecules are going to be causing the behavior of all matter. So that's within the human body, cooking, cars, and in all of science history, there really hasn't been an exception to this rule. The molecules really determine the behavior of that compound. So let's look at chemical compounds and chemical formulas. So if we look at water, H2O, that's a chemical compound, because it takes 2 hydrogen atoms bonded to 1 oxygen atom. Okay, and it makes a point here, though, this probably has other substances in the water other than just hydrogen and oxygen, because it's probably not pure deionized water, even out in nature. So here we see the 2 H's, the white ones on every oxygen. Okay, so that's the formula and how it combines. So the chemical formulas actually indicate the elements that are present in a compound and how many are the relative number of each atoms in a compound. So if we change the subscripts, which are these lowercase numbers here, if we change the numbers on a compound, it's no longer going to represent the same compound. It's going to have different properties to it. So H2O is water, but if I put on 2 oxygens instead of just 1, H2O2 is hydrogen peroxide, and it's going to have a much different reaction. Another thing we can look at here is this larger molecule, C12H22O11, which is one of the forms of sugar that we put in our coffee. Okay, so as we put on more hydrogens, more oxygens, and add in the carbons too, we have another compound. Okay. So this is pretty easy, all this concept check, and it doesn't all fit on the screen, but the question's there. So they want us to determine the number of each type of atom in glucose, which this particular molecular formula is C6H12O6. So it's just as easy as it looks. So these subscripts tell me how many atoms of each molecule are there. So let's look at the answer. I have 6 carbons, 12 hydrogens, and 6 oxygen atoms. So it's exactly what you thought. Okay, I'm going to slide this up just a little, if I can get it to move. There we go. Okay, so as we look at ionic and molecular compounds, which they're using the term molecular to go with covalent compounds, which means they're not a metal, they're non-metal compounds. So when we look at making up these compounds, any element with unstable electron configurations are going to form compounds with other elements because they're trying to get to stability. So what they're trying to do is they're going to transfer electrons, which is the ionic compound, or they share electrons within molecular compounds to get their outer valence shell to 8, or the octet, just like we talked about in column 18 with the noble gases. They have 8 electrons in their outer valence shell, so they're very stable, they don't change. So that's what these compounds are trying to reach, because their elements that make up the compound are not stable. Okay, so with an ionic compound, that will contain a metal and 1 or more nonmetals. And the example they use here in these slides are sodium combining with chloride, because the metal is going to be positive. So the metals and nonmetals are a very good chemical match, because metals will lose the electrons, they become positive. Nonmetals gain electrons, so they become negative. And the result is an ionic bond. And then any of the subscripts that we have on any of the elements that are making the compound will show you the ratio of how the elements form or bond together into a crystal lattice, so it's a much larger compound. Okay, so if we look at sodium chloride, so we've got solid sodium chloride, so we've got the sodium ions here that are looking more metallic and the chloride being green. And because we have positive and negatives, these are soluble ionic compounds. When they are dissolved in water, they're going to dissociate into the positive sodium and the negative chlorine ions. So I'm going to have a solution with ions in it, and it's going to conduct electricity. Okay, so this is just a physical change that's taking place. There's not a chemical change because it's still sodium chloride, it's just dissolved. Okay, now my molecular, or what we're also calling covalent compounds, they contain nonmetals only. Okay, so the electrons in a covalent bond, or molecular bond as they're calling it, are shared, but not always equally. So what will happen is the one with the stronger charge, the electron will tend to spend more time with the stronger charge and less time with the weaker charge, but it's shared back and forth, and that's called a covalent bond. Okay, so again, the subscripts, or those lowercase numbers, are going to tell us how many of each kind of atom are in the molecule, and these molecular or covalent compounds can be extremely small or very, very complex, such as some of our protein molecules. And here you can see this hemoglobin molecule. It's a pretty big molecule, okay, with lots of different portions to the compound. So if we look at the properties of these covalent compounds, or compounds without metals, okay, the bulk properties of these molecular compounds depend on the molecules that compose them. That's true of any compound. Okay, and the composition of the molecules in this compound actually is responsible for what happens. So it will be responsible for the atoms, the shape, the structure, the bonds. And the first example they use here is propane, which is C3H8, so we got carbon and hydrogen, there's no metal in there, and that's used as a fuel. Okay, but if we change it, I need to pull the slide down here so you can see what they say here. If I change it to C8H18, this is octane, which is pretty obvious because I have 8 carbons in here. So the octane, and this is part of gasoline, so it's going to respond much differently than propane. So just small changes going from the 3 carbons to 8 carbons, and we go from 8 to 18 hydrogens, that will dramatically change the properties of the substance and what's going to happen. So let's go ahead and do another concept check here. And what we have to do is classify each compound as ionic or molecular. So ionic will have a metal and a nonmetal, and the molecular or covalent will have no metals in it. So sodium bromide. Well, we've just been talking about sodium chloride being an ionic compound, so sodium bromide would be ionic. Carbon dioxide, I don't see any metals in there, so I'm hoping that's molecular. Magnesium fluoride, magnesium's a metal, so I'm hoping that's ionic. And I have carbon and hydrogen in my CH4, so hopefully that'll be molecular or covalent. So we have ionic, covalent, or molecular, ionic, covalent, or molecular, and that's what it is. Okay, so that's not real difficult. All right, so now what we do, now that we've determined if we're going to have ionic or covalent compounds, Now we need to start looking at the naming of compounds, and that's what we're going to go into in a very easy way before we have our exam. And anytime we name an ionic compound, the name is going to begin with the cation or the metal, and then the anion, which is at the end, will follow that using the base name of the anion plus the IDE ending or ide. So the NaBr is sodium bromide. So the bromine loses the INE and gains an IDE. Magnesium bromide is the MgBr2. And notice as I'm naming these that when we talk about an ionic compound, we do not put in prefixes to indicate how much of, or the numbers of each type of atom. When we get into covalent or molecular bonds, we do, but we do not do that in ionic bonds. So this is just magnesium bromide instead of a magnesium dibromide. Okay, so no prefixes in ionic bonds. Okay, now I have given you sheets, so those of you online, these are the sheets. It says an ion list, and they're kind of gray and white striped, and they've got monoatomic ions on one side and polyatomic ions on the other side. And so this is table 4.1 from your textbook, and these are some of the common anions or negative ions we're going to deal with. So we've got the nonmetal names over here, and here's our symbol for the anion, my base name, and then the anion name with the IDE after it. Okay, so that's not really that difficult. You just have to learn to recognize the symbols for each one of the elements. Okay, so we are going to name the following ionic compounds. So we won't be putting any prefixes in front of anything to tell us what each one is. So I have Li2O. Okay, if I look at that, that should be lithium oxide. For letter B, CaBr2. Ca is calcium, Br is bromine. So since it's attached to a metal, that would be calcium bromide. And letter C, K is for potassium, I is for iodine. So I add the IDE on the end of the iodine, and I get potassium iodide. So let's look at those answers and see, yes, we did get them all right. So good job. And since these are ionic compounds, we don't put the prefix di in front of it. That's only with covalent bonds. Okay, so here are some of our polyatomic ions. And notice the definition for polyatomic is ions that are composed of two or more atoms covalently bonded, so they behave as a single unit. So when we look at a carbonate and see CO3 2-, that 2- goes over the whole molecule. The bicarbonate, the 3-, excuse me, see now I'm getting it mixed up. That 3 is a subscript. That's only a 1-. Okay, that looks a little bit up there to me. I'm looking at a bad angle. So make sure you keep your subscripts down here for your number of molecules, and then, because you can see nitrate is NO3 1-, and phosphate is PO4 3-. So do make sure to keep those straight, because I almost made that mistake there. Okay, and sulfate is SO4 2-. So that whole sulfate molecule is the 2-. Whoops, I didn't mean to do that. Okay. So hopefully that becomes more clear as we work with it. So a concept check for this, name the following ionic compounds. So this would be magnesium hydroxide and sodium sulfate. Because I have a metal and a non-metal. So I don't name anything. But so these are my polyatomic ions that come in there. Okay, so one very common compound that's a polyatomic ion is calcium carbonate, CaCO3. So to figure out its molar mass, I look on the periodic table and see what the molecular mass is of calcium. I look and see what the molecular weight is of carbon, and then I look up the molecular weight of oxygen and multiply that by 3. So I add up all those weights, those molar masses, and it comes out to 100.09 grams per mole of calcium carbonate. Its melting point is 1339 Celsius, so that's pretty high since water boils at 100 Celsius. Very common in nature, and we use it in consumer products all the time. Okay, so now we're going to get into naming the molecular or covalent compounds. So usually they're nonmetals, but the element that's more metallic is listed first and is followed by the less metallic elements. And the prefixes in these are used to show the number of atoms of the element that are present. The only place we don't use the prefix mono is on the very first element. So if I have 1 at the front, I don't put mono in front of it. If the less metallic element is single, then I'll put mono in front of it. Okay, so let's see how we name these. So we've got carbon and oxygen. So carbon is my, if you have to call it my more metallic, oxygen is less metallic, and I have 1. So this would be carbon monoxide. Okay, does that make sense? And we'll look at these on the next slide too. So I've got N2O5. Okay, so I've got 2 N's. So dinitrogen. I've got 5 oxygens, so the prefix for 5 is penta. So it would be pentoxide. And actually SO3 is a sulfite, but we could call this sulfur trioxide as well, would be another name for it. So let's look at all these and their explanations. Again, no prefix for the 1 carbon, and we use mono to indicate 1 oxygen for carbon monoxide. We use the di prefix to indicate 2 nitrogens, and the pent suffix to indicate 5 oxygens. Sulfur trioxide, no prefix for 1 sulfur, and use the tri suffix to, that should be, they're calling them a suffix, but it's on the front of the word. That should be a prefix. So just realize you put it in front of the ide, but that, I just didn't realize they weren't talking about that correctly. Okay, so that's where we're going to stop because we're getting into atomic mass units, and we're going to stop here on this part of the lecture. So I am going to get out of the slides and let me get into the module. I want to find that handout that I told you about. I'll show you where it is on here. Okay, no, those are the lecture notes. Physical and chemical changes. Okay, so this is just a review of the slides that we looked at in Chapter 3. So we're just going to look at this very quickly. Oh, that's not very good. Okay, hopefully your copies look better than this. But the only thing I really want you to know is that a physical change is a change in which the substance changes form but keeps its same chemical composition. So it's reversible. A chemical change is where something new is formed and it's irreversible, like burning a piece of paper. Okay, going into ashes and CO2 and giving off water. Okay, so that's the physical and chemical change. And then the last thing on here, I'll go ahead and move this up, is just what exothermic and endothermic reactions are. Exothermic describes a process that releases energy in the form of heat. So when we form a chemical bond, it releases energy and is an exothermic process. So it's going to feel hot. Endothermic is a process or reaction that absorbs energy. So breaking a chemical bond requires energy and therefore is endothermic. So making a bond is exothermic, breaking a bond takes energy is endothermic. And that is all I want to talk about on that sheet. So let's go to the assignment that we started on Wednesday that I didn't have a chance to look at, and that will be this week too. Sorry, guys. Okay. Ag Chemistry 120, Chapter 2, Lecture Notes. Okay, and these are the slides I just covered. And then there'll be a quiz on this. I think I'll start with this on Friday morning, and then we'll finish up this this list. Okay, so I just need to open it up. And there's a lot of review in what we're doing, but that doesn't hurt as we go through this. Okay. All right. So as we look at this, I'm going to pull this down just a little bit. Notice what I put up here was coffee. And when I have class at 8:30, this is a good compound for me to look at as caffeine. Okay, so as we look at ionic or covalent bonding, we're looking at atoms or groups of atoms that may be charged. Notice that we have positive and negative charges. Electrons are negative, protons are positive. Neutral atoms have the same number of electrons as protons, so the total charge is 0. Okay, so on the periodic table, hydrogen has 1 proton. It also has 1 electron, so its charge on the chart is neutral. Okay, so everything on the periodic table has a neutral charge, the way it's listed. Okay, so now the different things we're going to talk about is we are going to actually today just talk a little bit about ionic bonds, covalent molecules, and then we'll get into compounds containing the polyatomic ions, and then some molecular mass or molecular weight at the end of, it'll be tomorrow's lecture. Okay, so compounds are actually made of 2 or more atoms of different elements that are held together by bonds. Okay, so what we're going to do is learn how to read formulas, subscripts, and coefficients so that we can determine the number of each type of atom present in a formula. So as we look at this, here's a subscript, the BR2, where it's a lowercase. So subscripts show how many of each type of atom or group is present. If there is no subscript, there's just 1 atom. So we have 1 calcium, 2 bromines. So calcium bromide. 1 calcium, 1 carbon, 3 oxygens. Calcium carbonate. 1 calcium, 2 oxygens. So carbon dioxide. Okay. So coefficients are always in front of a compound, like we would see here, 2 FeCl2. So they don't put a parentheses around it, but that's how it's read, is 2 of this whole molecule, 3 of this whole magnesium dioxide, or dihydroxide, excuse me. Or magnesium hydroxide. I read that wrong, I apologize. And 8 carbon dioxide. So even though it doesn't have it, that means it's 2 of that whole compound. So the parentheses here are used the same way they are in math, and you have a subscript after the parentheses to show that we have 2 OH groups present. So there's one Mg and two OH groups present, and there's 3 of that. 3 times. So MgOH2, MgOH2, MgOH2. So the subscript is going to multiply all of the atoms inside that parentheses. So the example, it wants to know how many of each type of atom is present. So I've got 2 times the whole FeCl2 molecule. So I've got 1 iron. So 2 times 1 means I have 2 irons. I have 2 chlorines. So 2 times 2 means I have 4 chlorines. 2 irons and 4 chlorines in this one. Let's see if I can write on here. There we go. So now for magnesium hydroxide, since that's got a metal and a non-metal, we have 3 mg's because I've only got 1 magnesium. Okay, for each one of the hydroxyl groups, I've got 2 O's and 2 H's. So I've got 3 times each of that. So I've got, whoops, plus, I'm getting it on top of each other. I need to erase that. Let's put that in there. I'm not doing so hot here. Okay. Excuse my writing. So we got 3O2 plus 3H2. So essentially, that means I have 6 O's and 6 H's up here. Okay, and in the final one, I've got 8 carbons, and then I've got 2 times 8, so I've got 16 O's. That looks like 160, but it's 16 O's. Okay, so that's as easy as that is. So if you have any questions, please be sure to ask me about that. Okay, so when we go into making these bonds, the main thing we have to remember is electrons are negative, protons are positive. So with an ionic bond, one atom steals electrons from another and becomes negative, and the other atom is then positive. So within the ionic compounds, they're composed of a metal, which is usually the positive ion, plus a negative ion, which is the anion. So when a metal and a non-metal bond, each ion has its charge indicated as a superscript, like here when it's not bonded. Yeah, calcium plus 2, CO3 minus 2, OH minus. But when they bond, the charge goes away because it becomes an ionic compound. So sodium is a plus 1, and when we have this isn't working right. When we have a plus 1, you don't have to write the 1 there if you don't want to. If you just write a plus or a minus, it's assumed it's 1. So we got sodium plus 1, Cl minus 1, joined together to give us a 0 charge of sodium chloride. So we start out with these ions, and they end up combining and making an ionic compound. And most of our reactions in chemistry are explained by either the charges, opposite charges attracting, or similar charges repelling each other, like magnets. Okay, so there's a lot to be explained by that. Okay, so let's look at this problem here. If we have an atom that has given up an electron in a reaction, so it now has 10 electrons and 11 protons, so I've got less electrons and more protons. What is its charge? Well, if I've got more positive than negatives, that means it has to be a positive 1, because I've got 11 protons and only 10 electrons. So if I go and look at the periodic table under for the atomic number of 11, I'm pretty sure that's sodium in the left column. So it's a sodium ion, and that would be written it would be written Na+, like that, because it's a plus 1. Okay, so our ionic compounds are very often referred to as salts. Okay, and the term that we actually form it is a formula unit. So calcium chloride, potassium carbonate. Okay, so you've got a positive and a negative. So when they're put into water, they can dissociate into the positive and negative ions. So the way they form, as we said before, all atoms want to be like a noble gas with 8 valence electrons. So they want that outer electron shell full with 8 electrons, except for period number 1. And then we only have 2 electrons in that very first shell. Everybody else has 8. And remember, atoms can gain or lose electrons to complete the valence shell with 8 electrons and form ions. Okay, if we generalize, metals are usually going to form cations by losing electrons. Okay, so they're on the left side of the chart. Cations are positive and have more protons than electrons. And the atom lost, E minus, remember the word cation has a T for plus. So it looks like a T, I guess. I was trying to think of what that is for. Anyway, so the nonmetals or groups of nonmetals form anions by gaining electrons. Since if I add more electrons, it becomes more negative. They have more electrons than protons. So the atom or group gains electrons to form a negative ion. Okay, so some of our rules we need to follow when we look at these ionic compounds. The symbol for an anion must indicate its charge. Okay, the symbol shows the atom or atoms forming the ion. It shows the type of charge, plus or minus. It shows the magnitude or amount of charge, and the superscripted or the lowercase values below the number following the atomic symbols indicate the magnitude and type of charge per unit. And you've got another site that you can go to, a website here that you can go to and look at an article about electrolytes. So the example here is sodium plus 1. This is iron plus 3. This is oxygen 2 minus. This is iodine 1 minus. Okay, so those are single ions. Okay, we're going to finish up here pretty quick. Polyatomic ions, a group of 2 or more atoms that stay together and act as one ion. Okay, so if we look at we're going to be working with these quite a bit in soils with fertilizers, sulfates, nitrates, phosphates, and use your polyatomic sheet to write these out for me. So the carbonates, that ion came down from here, a hydroxide, OH minus. I don't want to tell you them all. You'll find them on the back side of your well, it's on the polyatomic ion sheet, and they're all written out for you, and you're going to be able to use these on your quizzes. And ammonium, NH4 plus, is the only positive ion that we have. Everybody else is negative, okay, in our polyatomic ions, because iron is a single anion. All right, so go ahead and write these out for those of you at home. We did them in class. Let's see if you can. They're pretty easy. You just read them right off the chart. Okay, and we are going to pick up with right here on ionic compounds on Friday. So I will record this lecture. I hope to get it done earlier in the morning. So thanks so much, and I will, hopefully you can hear this okay. I turned up the volume some more. So students, please let me know if there's a problem with it. So here's to the second lecture on Friday that will finish this group of notes. Thanks, guys.